You know how electricity is supposed to work, right? You apply a voltage, and electrons flow straight ahead. Pretty simple. But what if some of those electrons could just take a sharp sideways turn, all on their own? And what if that turn behaved like a one-way street where the rules completely change depending on which direction you're going? It sounds wild, I know. So let's dive into this pretty fascinating discovery.
Really think about that question. You push electrons forward and some of them just veer off to the side. It almost sounds like it breaks the rules. Usually to get that to happen, you need some really complex materials or some very specific fields lined up just right. But it turns out this can happen at a very special kind of intersection, under a very specific set of conditions.
So to really get our heads around this, here's how we're going to break it down. First up, we'll look at the physics puzzle itself. Then we'll zero in on the special junction where all the magic happens. After that, we'll uncover this one-way street effect, explain why it happens by talking about something called symmetry breaking, and finally, wrap up with why this is such a big deal for the future of electronics.
Okay, so let's start with the heart of the mystery. You see, physicists have a pretty solid rulebook for how electrons are supposed to act. And according to that rulebook, this sideways current, well, it just shouldn't even be there.
So here's what the textbooks would tell you. If you take this special type of conductive material and apply a very specific kind of field to it, an out-of-plane Zeeman field, you shouldn't get any sideways current. Now, it's really important we're clear. This is a Zeeman field. It's a special interaction that talks directly to an electron's quantum spin. It's not just any old magnetic field. And according to the physics, all the forces should perfectly cancel each other out. Nothing to see here. Or so we thought.
So, it turns out the key to this whole puzzle isn't in one uniform chunk of material. Nope, it's at a very specific boundary, a junction where two totally different materials meet. And this is where the rules of the game get completely rewritten.
And here it is. This is our setup. It's actually pretty simple. On the left, you've got a regular, normal metal. Nothing fancy. But on the right, we have our special material, one with something called strong spin-orbit coupling. All the action, everything we're talking about, happens right at that dividing line, what's labeled here as x equals 0. The interface is what makes it all possible.
So, what is this special stuff on the right? It's called a Rashba metal. And what makes it special is that inside it, an electron's physical movement is directly tied to its quantum spin. You can just think of that spin as a tiny little internal magnet that every electron has. And this link between motion and spin, that's what we call spin-orbit coupling, or SOC. That's ingredient number 1.
And ingredient number 2 is the Zeeman field. Again, I want to be super clear here. This is not your everyday magnetic field. The Zeeman field is all about how it interacts directly with that quantum spin we just talked about, that tiny internal magnet inside the electron. So when we use this field, we are very precisely tweaking that spin property. Okay, so let's put it all together because this is the absolute key. And just a single uniform piece of that special Rashba metal, applying the Zeeman field does nothing. No sideways current. Predictable, boring. But when you create a junction by sticking it next to a normal metal and you only apply that field to the Rashba side, bam! Something totally new, something totally unexpected pops up right at that boundary. The junction itself is the catalyst here. And this brings us to the really cool part, the big discovery. This new sideways current that appears out of nowhere has this very strange and very useful property. It does not behave the same way going forwards and backwards.
Right. So just by building this simple junction and applying that specific Zeeman field, a sideways current just appears. It seems to come from nowhere. But when the researchers looked closer, they found something really, really bizarre about how it behaves.
Honestly, the best way to picture this is to think of a one-way street. The sideways current you get when electrons are traveling from left to right is completely different than the one you get when they're going from right to left. It's wild. This directional dependence is what physicists call a non-reciprocal effect.
And check out this graph. It shows you the effect perfectly. First, look at that solid blue line. That's the main forward current. See how it's perfectly symmetrical? Same going forward as it is going backward? Now, look at the orange lines. That's our sideways current. The dotted line is for one direction, and the dashed line is for the other. They're not even close. They are completely different.
So let's just nail this down. The main forward current, totally normal, behaves just like you'd expect. But that sideways current, it is fundamentally asymmetrical. It somehow knows which way it's going, and it behaves differently because of it. That, right there, is non-reciprocity, and it is the absolute core of this discovery.
So, we've seen what happens, which is amazing. But the billion-dollar question is, Why? Why does this happen? Well, the answer lies in a really deep concept in physics, breaking symmetry.
Okay, so just imagine this. In a normal, perfectly balanced system, for every electron that gets a tiny little push to the left, there's another electron that gets an equal and opposite push to the right. They all cancel out, right? So you get no net sideways movement. But when you apply that special out-of-plane Zeeman field, you disrupt that perfect balance. You break the symmetry, and all of a sudden those pushes to the left are no longer canceled out by the pushes to the right. And what's the result? You get a net flow, a measurable sideways current.
All right, so a weird sideways current that acts like a one-way street. You might be thinking, okay, cool physics trick, but who cares? Well, it turns out this is a huge deal. This gives engineers a completely new tool for designing and controlling electronics at the tiniest scales. And one of the most powerful things about this effect is that it's not happening all through the material. It's an interface phenomenon. It only exists in this incredibly narrow region, right at the junction where the two materials touch. And that localization, that gives you an incredible amount of precision and control.
And you can see it right here in the data. Look at this graph. The junction is at position 0. Whether you're looking at low energy, that's the solid blue line, or higher energy, the dotted orange one, you can see the effect just completely fizzles out as you move away from that boundary. It's a current that basically lives and dies right there at the interface.
So what's the big picture here? Well, we have a totally new way to generate and control electrical currents, and we can do it without needing complex setups, extra magnetic parts, or anything like that. This really opens the door to completely new designs for semiconductor devices, the chips inside our computers and our phones. It's a fundamental breakthrough in our ability to boss electrons around at the quantum level. So we're left with this incredible idea, a current that has its own built-in sense of direction, an electrical one-way street created right in the fabric of matter itself. And this just makes you wonder, could this newfound control be a key building block for the next generation of smarter, more efficient quantum-level circuits? The possibilities are pretty mind-blowing.